70 years ago, we found the key to the solar system. It would unlock affordable launches of thousands of tons at a time, rapid travel to all the planets and even beyond the solar system. But we decided not to use it. Nuclear energy. This isn't science fiction. Legitimate, feasible designs were tested and presented by scientists involved in the Manhattan Project in 1946. Their work had started in secret and first revealed to the world as a tool of terrifying destruction. Now they were eager to show off its peaceful purposes. Their plans would solve one of the greatest problems facing the rocket industry, the rocket equation. The equation that demanded chemical rockets to become massive stacks of fuel with huge expensive sections being discarded into the sea. Nuclear energy could solve a lot of this problem, but not through nuclear reactors providing thermal power to exhaust gases. This would be like drinking from a swimming pool through a straw. Efficient, but without the thrust needed to get large payloads off the ground. The world had witnessed the immense power nuclear bombs could deliver in an instant, equivalent to tens of thousands of tons of chemical fuel in a much smaller package. If these explosions could be harnessed for a rocket, they would transform how we got to space. But the only way to get a vehicle moving with nuclear explosions was to place it inside the fireball of an atom bomb. Most people today would assume everything is simply destroyed inside the hellfire and leave the insane idea at that. Scientists in the 50s had a different approach. This is how Project Orion was born, and this is its story. The first question the engineers and scientists behind Project Orion had to answer was what can survive a nuclear blast. The US military was very interested in this question. They needed to know how to build shelters to resist a nuclear attack, and in turn, how powerful their warheads needed to be to destroy hardened targets. The heat, radiation, and shockwave from a detonating nuke could destroy the other nukes in a volley too, so knowing how closely they could be spaced was vital. Answers would come from the many nuclear tests they were eagerly conducting, specifically the experiments that involved placing different materials at varying distances from ground zero of a nuclear device. One such experiment involved Lou Allen's balls. Lou Allen was an Air Force physicist who was worried about America's supply of tritium, a heavy isotope of hydrogen necessary to fill thermonuclear warheads. The first fusion bomb was detonated in 1952's Ivy Mike test, and it was quickly followed by plans for warheads of much larger yields, into the megatons, which needed more tritium. Allen knew lithium could transform into tritium after being bombarded by neutrons, and the radiation of a uranium fission bomb could do the job. So, he had these balls blasted by a 20 kiloton yield device to test that theory. Experiment Viper took 1 meter wide steel spheres filled with a lithium-containing material and placed them just 10 meters from the point of detonation of an atom bomb. The spheres would absorb the intense radiation without being destroyed, thanks to a graphite coating. Graphite was used because it has the highest vaporization energy for its weight of any solid material, allowing it to absorb a huge amount of heat energy before becoming a gas, which is why it is so commonly used in ablative heat shields. But two surprising discoveries were made as a direct result of these experiments. First, they discovered that when the balls were engulfed by the thermal blast of the warheads, a millimeters thick layer of graphite vaporized into a protective gas shield, allowing the spheres to withstand a 150,000 degree fireball without damage. And second, the spheres had been shot out of the fireball like cannonballs by the expansion of that gas. What if this phenomenon could be harnessed for a rocket? The idea didn't get much traction. That was until Sputnik sailed over the United States in 1957, kicking off the space race. Vast resources were quickly unlocked to fund efforts that would beat the Soviets in space, now and in the future, including less certain technologies with great promise. The Advanced Research Projects Agency was set up in early 1956, and Project Orion began under the same year. Papers detailing the physics of the principle became workable designs, and larger concept spaceships began to be planned. But Project Orion wasn't just sketches. Actual designs began to be tested, including a small rocket that was pushed to 100 meters in altitude by 6 explosive blasts. Another was a scale model that was exposed to repeated shock tests. Several spaceship designs of various sizes and purposes were drawn up, ranging from lunar Orions that went to the moon to 10,000-ton Orion ultra-heavy lift vehicles that carry their own weight into orbit with each launch. Each one would be a massive step ahead of the spacecraft of their time and still remain unmatched to this day, capable of crossing the entire solar system in a month or heading to Alpha Centauri in a human lifetime. But for the sake of this video, we will focus on one specific design, the 4,000-ton Orion ship, the first serious proposal from the project. It was to be a heavy lifter, a 78-meter tall bullet, able to deliver 1,115 tons into low Earth orbit, but also capable of delivering 300 tons to Mars and returning without refueling. Docking in space had not yet been attempted, so being able to send up whole space stations in one piece or perform entire missions with one vehicle was a distinct advantage. Declassified reports tell us how it would have worked, focusing on 4 critical elements. The first and most important element is the nuclear devices that would propel the spaceship. It couldn't be just any design, it had to be both small and powerful. Both the United States and the Soviet Union were trying to compete by building the biggest and most powerful weapons possible, but scaling up nuclear bombs is easy. Trying to make them work effectively at a small scale is much more difficult. Neutrons are needed to sustain a nuclear chain reaction, but they are highly penetrating and quickly leak out of an atom bomb. Smaller cores let go of more neutrons, so fewer fission reactions happen inside and much of its fuel is wasted. But this can be compensated for with higher explosive compression to increase density, and thereby increasing the chances of neutron collisions. But that comes with its own design challenges. The US was obsessed with inventing miniature warheads to fit on a new generation of submarine-launched ballistic missiles, to arm a new branch of the United States nuclear arsenal. The key was plutonium, a more volatile fuel than uranium, encased in beryllium that efficiently recycled and reflected neutrons. This was even used to create the Davy Crockett tactical nuke, designed to be launched by soldiers on the battlefield. This approach was perfectly suited to Project Orion's needs, and they quickly adapted the idea into the miniaturized nuclear bombs that would be lobbed behind the rocket, and they dubbed them pulse units. These pulse units would weigh about 1 ton each and release 25,000 tons worth of TNT. Half of the pulse unit mass, however, was a plate of tungsten. That plate was the difference between a bomb and a rocket engine. We know that nuclear bombs create intensely hot fireballs that rise off the ground as menacing mushroom clouds. But the actual output of a fission reaction is lots of X-rays, fast-moving neutrons, and a thin burst of plasma. Earth's atmosphere absorbs them within a few meters and turns them into heat. That's how the mushroom cloud is formed, as the heat rises and cools. In a vacuum, an atom bomb just looks like a flashbulb burning out. A mere spark followed by an invisible wave of radiation. Still deadly, but useless for moving things in space. A thick plate is added to the pulse unit to intercept the energy of the fission reaction, absorb it as heat, and explode out as a rush of hypervelocity gases. It is those gases that act like the exhaust of a rocket engine to propel the vessel in a vacuum. Tungsten was chosen because it did an excellent job of stopping harmful radiation from reaching the spaceship while being 10 times more compact than graphite. Project Orion's engineers also conceived of a way to channel the energy of a nuclear device so it would preferentially strike the tungsten plate rather than dispersing in all directions. A cone of beryllium oxide encased in uranium was able to absorb the initial release of energy from the nuclear reaction. The instant expansion of the beryllium generated a shockwave, and using techniques already known to engineers for how to turn explosives into shaped charges, like the anti-tank heat warheads, it could be redirected to push against the tungsten plate. With all inefficiencies accounted for, the pulse units would have an exhaust velocity of 36,000 meters per second, 10 times the exhaust velocity of a conventional chemical rocket. The pulse units would be detonated roughly once per second, releasing an average of 100 terawatts of instantaneous power. That's 5 times more power than all of humanity uses at any one moment today. But the engine's thrust was delivered in millisecond pulses, like hammer blows. While Project Orion's experiments did prove that a solidly built vessel could handle such jolts many times, some accommodations would be needed for a crewed Orion ship. A suspension system was the second vital element they designed. Facing the nuclear blasts was a 26-meter diameter steel disc coated in oil. Tungsten gases from the pulse units bounced off this pusher plate to transfer their momentum, while the oil acted as a sacrificial layer that prevented damage, a technique actually shown to work in real atomic tests. The pusher plate would then get violently slammed backwards into a gas bag. Like an airbag during a car crash, this bag would reduce the plate's acceleration from thousands of Gs to a few hundred Gs, which is still enough to crush a human instantly. So then, a 27-meter long suspension arm that contained springs and hydraulic pistons smoothened out and delayed the pushes into an average shove of 1.25 G. If everything worked out, it would be about as bumpy as driving down a country road. The gas bag and pusher plate kept on wobbling while the suspension arms moved through their cycle. Running down the center of the suspension arms was a pneumatic gun that shot the pulse units through the pusher plate every second, with a shutter closing behind the pulse units each time to protect it from the hypervelocity tungsten plasma moments away from hitting it. Finally, there was a question of storing the pulse units. Engineers settled on disc-shaped magazines, each holding 60 pulse units in ammo drums feeding into a delivery system. Adding Delta V to the Orion spaceship was a simple matter of stacking more magazines. Reaching orbit would consume nearly 600 pulse units, while a full mission to Mars with return would need 1,500. But it was because of this final element that Project Orion fell apart, not because its design was flawed. Project Orion was, in a sense, radioactive. It was pretty sound from an engineering perspective and offered a ridiculously huge step forward in terms of spaceflight capability, but from a bureaucratic perspective, it was impossible to sustain. In mid-1958, NASA was founded to take responsibility over spaceflight development from ARPA, which meant it took over Project Orion too. It took less than a year for NASA to decide it didn't want to deal with the secrecy and complications of handling nuclear explosives technology. So, it cut funding to Project Orion in 1959. It didn't help that NASA was in the process of investing billions of dollars into the creation of the Saturn family of giant chemical rockets to land on the moon. Project Orion was going to make all of that effort obsolete as soon as their work was done. One 4,000-ton Orion launch would match the total mass lifted into orbit by all of the Apollo launches. So, Orion was shopped to the Department of Defense as a project with military potential, capable of lifting an entire battleship full of ballistic missiles into space with no counter threat. Needless to say, it caught their attention. This was enough justification for funding Project Orion for 5 more years. During this period, the prospect of actually building and testing an Orion spaceship slipped away further. It became clear that a ground-launched Orion was no longer politically acceptable, as the public became aware of the fallout of all that nuclear weapon testing and would not realistically accept a launch vehicle that took off with hundreds of nukes over their heads. The project's engineers were forced to design much more modest vehicles that were light enough to be placed on a chemical booster, so it could be lifted up to a 76-kilometer altitude before starting its nuclear pulse cycle. The idea was that any fallout from the nuclear explosions would be dispersed harmlessly, with the majority leaving Earth entirely. But this obviously wasn't terribly safe either. A full safety study was conducted. It found that high-altitude detonations would produce significant electromagnetic pulses, strong enough to knock out nearby satellites. Risks like an early pulse detonation destroying the ship's pusher plate or a misfire leaving the suspension cycle out of sync were also highlighted. A fully loaded Orion exploding on the launch pad was a terrible possibility too. The worst case scenario, however, would be a failure during the climb to orbit. A nuclear chain reaction wouldn't happen, but it was possible to set off the high explosives needed to compress the fissile fuel in each nuclear pulse unit and scatter radioactive material over thousands of kilometers. Addressing these problems drastically cut into the potential performance of an Orion vehicle, while making it much more expensive to launch. Compensating for the less impressive performance of these later designs, is perhaps why Project Orion under the US Air Force leaned on the military aspect, leading to some crazy creations. The Emergency Command and Control Orion was a 2,500-ton design sitting in a silo like an ICBM, but it would only be launched in the case of a nuclear war to become a flying NORAD backup. The Doomsday Orion used its payload capacity to place a 1,650-ton thermonuclear weapon in low Earth orbit. It would have a yield of 8,250 megatons, matching all of the American warheads combined, and be able to set a land area larger than France on fire just by detonating in space. Another military version was reportedly presented to President Kennedy, only for it to be rejected as horrifying and unnecessary. It's easy to discount these ideas as absolutely batshit insane now, but these were the 50s and 60s, an era when dozens of nuclear tests were being carried out at home and abroad every year, where nuclear reactors were flown on aircraft and nuclear thermal rockets were tested to destruction in open air. Soldiers were watching nuclear explosions from trenches. OSHA didn't even exist yet. Project Orion itself was secret throughout its life, and most details remained classified for decades afterwards. If circumstances were different, it could have gone ahead. It was actually the changing international situation that finally killed Project Orion. The United States and the Soviet Union suffered the 1962 Cuban Missile Crisis and started diplomatic talks to prevent a similar escalation from happening again. Part of those diplomatic efforts were mutual agreements to limit where and how nuclear weapons could be tested, culminating in the 1963 Partial Nuclear Test Ban Treaty. Signing it meant that nuclear bombs could no longer be detonated at high altitude or in space. That was the death knell for nuclear pulse propulsion. While the pulse units that propelled an Orion spaceship weren't technically bombs, they looked very similar. Building an Orion, let alone testing it, would mean manufacturing thousands of self-contained nuclear explosives at a time when the world powers were trying to restrain the growth of their warhead stockpiles. Worse, an Orion launch would trigger nuclear attack alarm systems all over the world, and with only the reduced performance of a chemically boosted design to show for it, it was no longer tenable to continue working on it. With that, Project Orion ended in 1965. The dream of a vehicle riding nuclear blasts into space, however, did not disappear. Rocket engineers could not let go of such a massive leap forward in performance. Project Orion veterans tried to keep their dreams alive by showing it off as soon as it was declassified to Arthur C. Clarke and Stanley Kubrick during the early development of 2001: A Space Odyssey, and later by continuing to work on it in their own way. A lot of research has been done on nuclear pulse propulsion since the 60s, accelerated further in recent times by computer simulations that can take the place of forbidden nuclear tests. That has resulted in a fair number of improvements and modifications to the original Orion design. It's widely agreed that no pulse propulsion system should ever detonate nuclear explosions inside the atmosphere. Instead, it should be a vacuum-only vehicle that's delivered into space using conventional launch vehicles. Orbital rendezvous, a tried and tested technique for assembling spacecraft out of smaller pieces, got Apollo to the moon and can be used again to grow a full-sized Orion out of many small launches. Advances in material technology can make it much lighter than estimates from the 60s too, while the latest suspension systems can make the ride smoother and more resistant to misfires. But perhaps the most important innovation, one that can let us imagine reviving Project Orion today, is the way nuclear explosions happen. The original concept for nuclear pulse propulsion used pulse units adapted from small warheads, a near critical mass of plutonium compressed by high explosives. Since then, we have found ways to ignite much smaller amounts of fissiles without using any explosives. The concept is microfission, and it uses tiny fuel pellets, less than 100 grams, compressed magnetically by an external electric field. That current would be delivered by stacks of supercapacitors, coming down superconducting wires and then flowing across thin transmission lines into the pellets. When this much current passes through a conductor, a strong magnetic field is generated, enough to destructively squeeze the conductor and compress the fuel to ignition. This would release energy equivalent to about 0.01 kilotons of TNT, far smaller than any Orion pulse unit. But the second key new technology is the magnetic nozzle, which can catch and redirect the superheated vapor created. With the pulses so slight, a much more modest suspension system can handle them without gas bags or long exposed arms. Even better, the magnetic nozzle has the advantage of being able to extract energy from the exhaust plasma rushing through it, so it can recharge the capacitors ahead of each pulse. In 2003, the Minimag concept was actually tested at the Sandia National Laboratory's Z machine, which is able to provide the tens of millions of amps necessary to compress a fuel pellet. Its designers wished to use curium-245 as the fissile fuel, an isotope with an exceedingly small critical mass, but we can imagine a variant using more common uranium-235, perhaps not even at weapons-grade enrichment. A full-scale Minimag Orion spaceship would have had an exhaust velocity 40 times better than any chemical rocket, while enjoying 1g acceleration and a delta V on the order of 150 kilometers per second. That's enough to get to Mars in 10 days, or reach Jupiter and return in under a year. Its disadvantages, such as requiring hefty electrical ignition equipment and being unable to operate inside an atmosphere, can actually be construed as safety benefits for a public warier of nuclear energy than ever before. But is this all enough to revive Orion? Is incredible performance, new safety measures, plus modern improvements enough? There may be one final obstacle. Orion would be a novel, high-performance propulsion system that needs a lot of funding to become real. It would only get that funding from the likes of NASA or the Department of Energy if it met their needs for an intensive, high delta V mission. But such mission requirements do not exist because fulfilling them with existing propulsion technology is too difficult. No one is seriously talking about sending astronauts to Jupiter anytime soon, because getting there with chemical rockets is such an enormous task, which means Orion doesn't have a mission to justify. It's a chicken and egg problem that has trapped many other innovative space technologies, from laser light sails to advanced plasma thrusters. In the long run, technological development in unrelated sectors might get NASA to adopt nuclear pulse propulsion. Perhaps a portion of the resources used to pursue magnetic compression of fusion pellets could be diverted to microfission research, like how progress in making solar panels lightweight and efficient got them to be used in deep space probes. Or competition in the short term could be the trigger for reviving Orion. It was competition from the Soviet Union that accelerated space development in the first place, and in the future, the United States might look again for technologies that keep it far ahead of countries like China. We can only speculate if or when this happens, and it may take many more decades. But nuclear pulse propulsion remains a massive leap forward, just waiting to happen. It may take decades before we know if Orion or anything like it will ever leave the drawing board. But history has shown us that the boundary between bold scientific ideas and public controversy can be razor thin. Sometimes a single piece of research can ignite debates that stretch far beyond the lab reshaping politics, media, and even public trust in science itself. That's the story behind 17 Pages, a new feature-length documentary on nebula. It unpacks one of the most dramatic scientific ethics cases of the 20th century, an event so explosive it was dubbed the Scientific Watergate. What began as a routine co-authored biology paper escalated into a national scandal, with whispers of fraud, political agendas, and a high-stakes investigation that reached the halls of Congress, and even caught the attention of federal agencies. Through never-before-seen interviews, gripping footage, and congressional testimony, 17 Pages explores and reconstructs how bias, media spectacle, and public perception reshaped the fate of the scientists involved. The deeper the story goes, the more it challenges what you think you know, not just about science, but how truth gets decided when politics and personal reputation are on the line. And it's only available on Nebula. That's where I and a growing group of creators are releasing original, thoughtful, ad-free content that goes much deeper than what the algorithm wants. And I love YouTube as much as the next person. It's where I forge my career, and I plan to post here long into the future. But I think we have all seen where the platform's priorities are going. When I search for a video sometimes, only shorts show up. When I look at my homepage, it's getting increasingly cluttered with AI-generated crap with inaccurate scripts and fake robot voices. I genuinely think that platforms that don't police this mass-produced, low-quality content will just become increasingly less useful. When we can't tell what's real from fake, I think the only logical solution is to disengage. And I view Nebula as a sanctuary away from all that noise, both for creators and the audience, only working with the best creators that take pride in their work, because they love their work. Bobby Broccoli is one of the highest quality channels out there. I know what you're thinking, not yet another subscription service. So, if you really don't want another reoccurring payment, we've made it possible to buy a lifetime subscription to Nebula. I think all the documentaries and shows on Nebula are worth $300 right now, but this is a lifetime membership, so you will get access to Nebula and all the future things we make as long as Nebula exists. So, if you want to support creators who still value craft and get access to some of the best video essays and documentaries on the internet, head to nebula.tv/real-engineering or click the link in the description or scan the QR code on screen to sign up. You'll get 40% off an annual subscription. That's $36 for the whole year. Watch 17 pages now, only on Nebula.